A couple of last ideas that can be used when integrating. Symmetry is a great option for us, and we've seen this, that if we've got an even function negative x is equal to function x. When it comes to integration, well, from minus a to a would be the same as going twice from 0 to a. We know that. That idea can be used in other situations. If I had something like this, if we have shifted the symmetry, that's basically what we're saying here. Instead of going from minus a to a, it's going from c minus a to c plus a, but it's still going the same amount either side of the point. Then that would be the same as twice c to a, if it's symmetric about there. So it still has to be symmetric around that axis. It still has a vertical axis of symmetry, the shape. It's just at a different point. It's not at 0. How useful is that one? Yeah, probably not a heck of a lot, to be honest with you, because you're still going to have to integrate anyway. Maybe it would have been just easier to go from the original a to b, whatever it happened to be. But odd function idea, though, it can be more useful. Because remember, with an odd function negative x is negative function x. That means when we've got a symmetric shape, we know it's equal to 0. So in this case, even if there's a shift on, if we spot that rotational symmetry about a point, I don't have to do any integration. I can say, oh, hang on, that's going to be 0. May not occur a lot, but gee, if you do spot it, that can save you some time. The third one, again, it's a particular situation, but it's kind of neat way of simplifying integrals down. If you're integrating from 0 to a of a function, it's exactly the same as if you integrate function a minus x. Let me just prove that for you. Let's start with function a minus x. I'm going to show you, yes, it's the same as integrating function x. And what do? I'll do a substitution. I'll let u equal a minus x, so du is minus dx. That means my limits are going to change, so you notice I've actually swapped around. But sub in, I get, well, a minus x, that's u, dx is minus du, and the limits have swapped round. But one thing we know is that negative, I can take the negative away and swap the limits. So it now becomes the integral from 0 to a of function u du. But it's a definite integral. So the pronumeral is irrelevant because we're going to be substituting it anyway. So that's the same as function x dx. So it can be handy, that one. All right, and keep in mind this, when you're looking at functions multiplied together, if they're the same type of function, so they're both odd or they're both even, you end up with an even function. If they're different types of functions, so one's odd, one's even, you end up with an odd function. But when we get something like this, then that's when that idea becomes useful. Sine cubed, sure, we've got techniques how we can go and integrate sine cubed. But if we notice, oh look, it's going from minus 1 to 1. We've got that symmetry. And sine cubed is going to be an odd function, because you're saying odd times odd times odd. Well, odd times odd, that's even, and then even times odd, you're back to odd again. I've got symmetry in an odd function, that's just equal to 0. I don't have to waste all that time doing the actual integration. I can go straight to the answer. 0 to 1 of x squared root 1 minus x squared. Okay, 0 to 1. So the key you're looking for is it goes to 0 to a number, but then you see that same number minus the x. So 1 minus x. It means you can swap the x and the 1 minus x around. And I'll change it to be 1 minus x squared root x. Why do that? Well, because now I can just expand that out. See, when it was root 1 minus x, I couldn't expand that out. But this I can. Add 1 to the power over the power, substitute in, and we get our answer. So when you're going to 0 to a number, you can always swap the x and that number minus x. Improper integrals. So an improper integral is when you're integrating somewhere it's undefined. So it might be going to infinity or something like that. Limits. This will tell us if a solution exists. Let's look at this one. Now, hyperbola. If we wanted to integrate from 0 to 1, and of course you can't have 0 on the bottom of the fraction, and it's not in the domain of that. So what on earth would we do? Okay, well, let's investigate. I'll just put an n there and say, well, look, n's approaching 0. What's happening? Now, if I was to integrate, I'll get log x. So I end up with minus the log of n as n approaches 0. Substitute in log of 0. Well, log of 0 is still undefined. So that one's no good. You couldn't do that integral. What about this one? 1 to, say, infinity. X e to the minus x squared. Okay, again, I can't really do infinity, so I'll say, well, okay, let's make it the limit as n approaches infinity of 1 to n of x e to the minus x squared. Integrate x e to the minus x squared, and we get e to the minus x squared. So now, let's think about that limit. The curve e to the minus n squared. So that's our backwards exponential. E to the negative power, n squared means I'm going to be positive, but negative n squared, it's always negative. What's happening as n approaches infinity? Well, that curve's approaching 0. So that limit does exist. Therefore, I've got an answer. Because that part will go to 0, so I'll just be left with minus a half times e to the minus 1, or 1 over e. We get 1 over 2e. So we use our limits to investigate these sorts of things. And then the final idea, which we have talked about before, is using area and inequalities to try and trap solutions and things like that. And this is basically using our idea of saying, hey, we can apply functions so long as things are always increasing, decreasing, things like that. But it's also true with integration. If you've got this inequality here, gx is less than function x is less than h of x, then I can say, well, that means the integral of each of those must also be in that same order. The area under those curves would follow the same pattern. Let's have a look at this old question now. So n's a positive integer bigger than 1. The area of the region under the curve, y equals 1 on x, from n minus 1 to n, between the area of two rectangles. So they've drawn the inner rectangle and the outer rectangle for us in that section. We have to show this particular inequality. As I say, they gave me that big hint by drawing the rectangles of how to attack this question, so I'm going to use that idea. I know the area of the inner rectangle will be less than the area under the curve. It's going to be less than the area of outer rectangle. Okay, the inner rectangle, well, we can look at that and go, yep, that's going to be 1 times 1 on n. The outer one will be 1 on n minus 1, and in the middle, well, it'll be whatever the integral is, going from n minus 1 to n. So I can calculate the two endpoints. I'll integrate the middle one, that goes to log sub n, so log of n over n minus 1. Alright, get rid of the fraction. Let's multiply both sides by n. N on, ooh, that's the same as that. Okay. Oh, and look at the power of that exponential. You've got negative of n on n minus 1. Alright, some of the pieces are starting to drop out. If I want to get to e to the power, I'm probably going to apply the exponential function to everything. Now, the log, if I go e to the log, I can cancel, but n log I can't. So it kind of makes sense to bring that n inside the log. So we'll make that n on n minus 1 to the power of n. Now I know e to the x is continually increasing, so I can apply that function to each piece of this inequality. So we'll make it e to the power, so e to the power of 1, e to the power of log cancels. I've got my n on n minus 1 to the power of n. And on the right hand side I get e to the n on e. Ooh, it's sort of backwards. Hang on. If I turn all three things upside down, it will swap the inequality around. If I write it so it looks proper, so that 1 on e now would go to the right hand side. Well, 1 on e is e to the negative 1. And here I've got the reciprocal of e to the power of n on n minus 1. Well, that's a negative index, and that's where the negative n, so that bit's okay. In the middle, I've got the reciprocal of n on n minus 1, which is n minus 1 on n, but that is 1 minus 1 on n. Bang, we've got the result, it's dropped out. In our notes, I've added a few things there. The old Cambridge, I've grabbed some questions out of that. Note, they used 2a minus x instead of a minus x in that substitution of the integral, but it's essentially the same thing. Exercise 4a, and of course, no Extension 2 student ever does this course without looking at the 100. But of course it would be very, very mean to make you do a 100. So you don't have to do number 78, okay?